Welcome back to another lecture in the series of sensor arrays and imaging course. In the last few lectures, we were discussing about one of the fundamental reconstruction algorithms in creating an image out of an array of sensors or transducers or antennas, which is the delay and sum beamforming. So time has come now for us to actually look beyond delay and sum beamforming. What are the other options available? And in this lecture we will be talking about one such algorithm, which is a non-linear algorithm, a non-linear beamforming algorithm known as delay, multiply and sum. Okay, so that's why it's called as DMAS. Okay, so let's discuss on this. Okay, so moving ahead, just a quick review of delay and sum beamforming again. So it can be nicely summarized by this expression, where k is nothing but the pixel number. So k, you have to calculate or you have to estimate the delay and sum output for each and every pixel in the image grid. And then of course the two important aspect is basically the for that pixel, what is the contribution from each and every sensor. That's why we vary the I from 1 to NC, where NC is the number of transducers or number of antennas in the array. And then xik of t minus tau ik. So tau ik is nothing but the delay, okay, the transmit plus the receive delay from the pixel k to the transducer I. And then xik of t minus tau ik is basically the expected signal, okay, expected signal which is supposed to be received by the transducer I from the pixel k. Okay, so that's the meaning of it. And then of course some people call this as the delay compensated signal, because we have the raw signal which is there for each and every transducer, and then based on this particular formula for tau ik, which we know is based on Euclidean distance divided by the speed. So that particular delay, moment you identify that, you can estimate what is the expected signal corresponding to that pixel for each and every transducer, right? So that's the meaning of this. And as I said, some people call it as delay compensated signal. And then of course we do have that signal for each and every transducer. How shall I weight that signal for each and every transducer? Shall I equally weight them, or shall I weight them with something? So that is what this weight WIK, which means for each transducer, for each pixel, I do have a weight, and we call in signal processing terms the name apodization to it. So basically delay and sum means you delay the signal corresponding to each pixel and each transducer, you weight them, and then you sum them together. So that's why it's called delay and sum. Okay, but the major takeaway which we didn't emphasize in the previous lectures is this weight WIK for delay and sum beamforming. It depends just on geometry, right? And we generally fix an f number, and f number is given by depth by aperture. So for particular depth, which is same as the time multiplied by the speed, and we choose an f number, based on that we choose an aperture. So that aperture opens up basically how many transducers you have to select, and then you can use a Gaussian or a Hamming or a Hanning shape, so that the shortest sensor to the pixel will be added or given the highest weight, and so on. Okay, so but overall the major takeaway is this WIK can be prior calculated, because it is just dependent on the geometry. Okay, there is no other dependence on it. So in terms, just to summarize delay and sum beamforming on a very high level, all pixels are under focus. Okay, so that is one important thing. So the reason is we are calculating for each pixel the delay to each and every transducer. So that means it's literally something like you are putting each and every pixel under focus. And some people, because of that reason, some people call the delay and sum algorithm as dynamic receive focus delay and sum beamforming. The why dynamic receive focus is because each and every pixel is assumed to be under focus. The reason is because you are calculating the delay, right? You are calculating the delay the signal takes from the pixel to each and every sensor. So that means the travel time, right? Actual travel time. So that means it's something like you're assuming that point to be in focus, right? So that's the meaning of it. So that's one important aspect. And another aspect is, as I said already, apodization weights, the WIKs, are just geometry driven. It's non-dependent on data. It doesn't depend upon the XIK value at all. So now I hope you are understanding where I'm going to. So let's actually now think about utilizing the data that we have. We do have xik, that means for each transducer and for each pixel I have the data. And shall I use it? Shall I use that data to come up with the apodization weight? So that is the literal meaning of it. Okay. So with this motivation, we comes to this topic of delay, multiply, and sum beamforming. Okay, so the name actually suggests it. It's quite straightforward. So what we are going to do actually is here, for example, so we do have two summations instead of one summation. And if you see, observe carefully, what we are doing over here is the I is varied from 1 to the last sensor minus 1. That means not the last sensor but just the sensor before that. And then J is varied from I plus 1 to the last sensor. So that means when I equal to 1, J is equal to 2. When I equal to 2, J is equal to 3. So that means I am going to basically or you can put this way, you have if you think from a coding perspective, you think of two for loops, right? One is actually going from 1 to nc minus 1, the other one is going from I plus 1 to nc. So basically, let's say I is equal to 1, then this will go from 2 to nc. When I is equal to 2, this goes from 3 to nc, and so on. So and then what is happening inside is very interesting. You are multiplying basically the subsequent channels. Okay, so xi and xj, they are subsequent or what you call neighborhood channels. So you first multiply, when I, let's put I is equal to 1, okay, then j is equal to 1 to nc. So that means x1, this part remains same, but then this guy will be x2, x3, x4. That means x1 will get multiplied with x2, x1 will get multiplied with x3, x1 will get multiplied with x4, and so on. So basically it's something like you are multiplying the the delay compensated data from one channel with all other channels. So you are not doing self multiplication, but you are doing sort of multiplication with all other channels. So similarly, when I equal to 2, it gets multiplied with 3 onwards, all other channels, right? And that's really interesting. This sort of cross multiplication, some people call it as sort of a correlation that we are doing, except for the self correlation, everything else. And of course, when we do x12, we need not do x21 because that's the same, right? So that's why this formula works. So ideally speaking, let's say I have I'm just trying to explain to you this concept. Okay, so I have, let's say 4 sensors. Okay, so my sensors are x1, x2, x3, x4, 4 transducers to start with. Okay, and then for each of these transducers, I will of course find the delay compensated signal. Let's assume they are x1, x2, x3, x4. So this formula basically suggests only this x1, x2 plus x1, x3 plus x1, x4. That's it, done. And then you go to x2, so x2, x3 plus x2, x4. So that's it, done. And then of course you have the last one, which is x3, x4. Okay, so this is what this formula does. You just cross multiply the sensors with all its neighbors except self, and then of course you don't need to do x2, x1 because it is same, right? You're just multiplying. So x1, x2 is exactly equal to x2, x1, so you don't need to do the other option. So x1, x2 is exactly similarly x1, x3, if it's already done, you don't need to do x3, x1. That's why this formula works. Okay, so just to reiterate what I'm saying, you do multiply one channel with all other channels except self. Okay, self multiplication. You are not going to do x1, x1 or x2, x2 or x3, x3. That's not done, but the neighborhood multiplication is done. Okay, so that's what exactly the delay, multiply, and sum, the literal meaning of it. So you delay, that means delay compensated signal we are obtaining, then you multiply across the channels, and then you sum it up. Now there are two issues in this particular formulation which is very important for us to understand. And by the way, this is really not a textbook stuff, this is actually an advanced stuff, and you can find all details of this algorithm in these two papers. It was originally proposed for microwave imaging way back in 2008, and later on proposed or redone and proposed for ultrasound imaging in 2014. And these two are top journals in the field. Okay, so it's very important that if you have any questions or clarifications, please go and refer to these documents, particularly the second one, which is much simpler for you to understand. Okay, so coming back here, as I said, this is cross multiplication with all the other channels except itself, and then you sum it up. But then there are two issues in this formulation. So one issue is basically, okay, so let me actually reiterate this using more confined animation than everything together. So just give me a moment. Yeah, so basically one important issue is this: the signal is squared, right? I mean, you are multiplying xi with xj, so basically sort of squaring the signal. Effectively the amplitude is squared, and hence the resultant signal is actually not an amplitude signal, but it is a power signal. So that's a problem. So how to solve that? Yeah, I mean, as you guessed it correctly, we need to do a square root operation. It's mandatory. So this formula, as I written it here, it's not the way we do delay, multiply and sum, because this is a power signal. We need to actually take a square root of this, but then square root, there is chance of negative numbers here, so square root of a negative number doesn't exist, so you have to do a slight trick. Okay, so let's actually try that out. And then multiplication. Yeah, I mean, typically we assume that first channel, second channel, third channel, everyone is actually transmitting the same signal at a certain sender frequency f0. So if you multiply two such channels with sender frequency f0, you just assume it to be, let's say, cos omega 0t into cos omega 0t, then you're going to get a cos square omega 0t, which is actually nothing but 1 plus cos 2 omega 0t. What I mean actually is, let's assume that the signal can be expressed in terms of cos omega 0t, let's say whatever number you have. Okay, so that means x1 is this, and x2 is also a variant of the same, right? I mean, of course there will be some small phase shift and all, which we will ignore. So then x1, x2, what is going to happen is omega 0t will be the term, and this is nothing but cos 2 omega 0t, right? So this is a baseband component at omega 0 equal to 0, and this is at 2 omega 0. So you will have, as a result of multiplication, you will have two new components in the signal. So one is basically this guy, centered at f0 minus f0, 0, that is this term, baseband we call in communication terminology. And the other one is f0 plus f0, which is 2f0, which is actually corresponding to this term, which is actually harmonic frequency. So that is very interesting. You had a signal at f0. Now after this multiplication operation, you are going to get one at 0 and one at 2f0. Oh, that is very, very interesting. So then of course we need to separate them out. We need to work on the 2f0 component only, and for that we need to have a band pass filter, right? So there is a band pass, there is an additional operation required after this multiplication, which is like to extract a 2f0 component alone and isolate it from the baseband component, the zero frequency component, and that for that reason we generally use the band pass filter. So that's an additional requirement that is coming up compared to the standard delay and sum algorithm. Okay, so let's move on now. Coming back to the corrected equation, so assuming this the shortened representation, let's say xi of k, the delay compensated signal corresponding to ith transducer and kth pixel is represented by sik, and that corresponding to the jth transducer and kth pixel is represented by sjk. Delay, multiply and sum beamforming algorithm can be summarized in this beautiful expression. So this part remains same, everything is same, except now, as we said, we need to take the square root. So how are we going to go about it? Actually, you take the absolute of this product, take the square root of that, and then multiply that with the sign of the product. So that way you will preserve the original sign of the signal, and at the same time you are now having an amplitude signal and not the power signal. So it's quite straightforward. There's nothing magic about it. What we understood by the max part of it, now we are trying to overcome those limitations using the improved formulation. Okay, now this is how we realize, as I said, for engineers maybe a better representation is not the mathematical equation, but rather the block diagram representation of the signal or the beamforming algorithm. So here, just to go from left to right, you have x1 of t, which is the raw channel data corresponding to sensor number 1 or transducer number 1. Similarly, x2 of t, x3 of t exist, and then you need to do the delay compensation or the delay shift corresponding to the pixel that you are interested in. So let's assume that it will be tau1, tau2, tau3 corresponding to a pixel k and corresponding to each of these transducers. So you identified that data, and that is nothing but s1 of t, just like we did it over here, s1 of t, s2 of t, s3 of t, and then you do cross multiplication. So s1 of t multiplied with s2 of t, and s1 of t multiplied with s3 of t, and s2 of t multiplied with s3 of t will come in the next step. Okay, so that's the thing. So this is only with respect to x1 that we are showing here. Then you have to repeat it for x2, x3 and so on. And then this part is nicely summarized here. You take the absolute, you take the square root of this multiplying result, and then you take the sign of that and multiply with it. So this part is basically summarizing this expression. And then of course you need to sum them together like this. That's what actually how. And then don't forget, as we said, you will have two frequency components here, one at baseband and one at 2f0, and I'm only interested in the 2f0 component, which I will use a band pass. BP stands for band pass filter to extract the 2f0 component. So this is the formulation. So compared to delay and sum, now we will come back and analyze it in more interesting way. Okay, so mathematically I hope you understood it, what is happening. Now intuitively, what is it going to give us? Okay, what is that extra that I'm going to give it? Because if you notice it, the apodization term is missing from this equation, right? There is no apodization, and that is the beauty about this, because there is a natural apodization happening. Because effectively, if you think, you are multiplying a signal with a signal from a transducer with signal from another transducer, what is happening is you are sort of cross correlating the transducer values, right? You are cross correlating x1 with x2 when you do x1 and x2, and similarly you are cross correlating with x1 x3. So there is automatically some weight happening, because x1 and x2 will be weighted by its similarity, will be weighted by its correlation automatically. You don't need to do anything, because if x1 and x2 are different, they will automatically get suppressed. If x1 and x2 are in line, in phase, they are high values, they will become much higher values after x1 and x2, right? Multiplication. So it's sort of projection. People call multiplication as always a projection of similarity enhancement, because two similar signals will get enhanced and two opposite signals will get suppressed. That's what going to happen after multiplication. Okay, so two insights that I would like to put across to you. So this operation, whatever we are doing over here, the delay, multiply and sum operation, can be mathematically interpreted as an autocorrelation function, or in the strict sense, I don't know why they are calling it as autocorrelation, because in the strict sense you are not doing x1, so it's not really autocorrelation, it's a cross correlation function, but they are mentioning it here. So the autocorrelation function of the receive aperture. Okay, so don't get confused by too many technical jargons here. Receive aperture means it's the receive sensors, receive transducers. So autocorrelation function across the transducers, across the antennas in the array. Okay, and receive aperture is chosen because we may not use all the transducers or all the antennas in the reception, right? You may choose an aperture and then you are not going to use all the transducers. That's why it's a generalized term, but you just need to think of it as something like you are cross multiplying across the transducers. That can be interpreted as an autocorrelation function with the transducers, except the auto product terms are excluded, right? We are not considering x1 into x1, x2 into x2, x3 into x3. All these terms are discarded forever, so we are not going to consider them. And also one more thing, the coefficients are halved. Okay, because you remember, if I calculate x1 into x2, I'm not going to calculate x2 into x1, because conventional autocorrelation is something like you do everything with each other in both ways, right? Let's say x1, x2, x3, x4 you had, then conventional autocorrelation means you will do x1 into x1 plus x1 into x2, then x2 into x1, then x1 into x3, then x3 into x1, all the things you calculate. But in this case, we are discarding the autocorrelation term, as well as we are discarding the repetitive terms. Like x1, x2 is done only once, because x1, x2 is same as x2 into x1. It's a multiplication, right? So we are not going to calculate x2 into x1 again, because x1 into x2 is already done. So that's what exactly mean. It is an autocorrelation function, but you are removing the auto product terms as well as the coefficients are halved. Okay, so that's the major interpretation, very important interpretation. And then in practice, okay, so some more intuition. In practice, if the aperture is not apodized, that means I'm not weighting the transducer, WIK, let it be 1. Okay, so I'm not going to give an extra weight to the transducers. If that is the case, you can safely assume that it's a rectangular aperture, right? It's a rectangular function. All the transducers are equally weighted, x1, x2, x3, x4, all are equally weighted. So now you can imagine this operation as a correlation between a rectangular window with itself, right? Because x1, x2, x3, x4 all are equally weighted means it appears like a rectangular window. If you correlate that rectangular window with itself, so basically when we say correlation, I think for computer science people might not have studied it. So correlation or convolution operation is basically you have a rectangular window like this. If you do autocorrelation with this, it means basically you move the same window to this side and then slide it in. Each slide you add the values together. Okay, so you first will not have any overlap. Now I'm touching it here, then you move it, move it, move it, move it, move it. Each movement you calculate the product and then sum it up. If you carefully observe it, it looks like a triangle. The correlation will look like a triangle. The correlation between autocorrelation between a rectangle window and by itself will look like a triangle function. But then here there is a problem, because the auto correlation we are not doing. We are not actually aligning them and doing a correlation, right? We are not doing x1 into x1, x2 into x2 and so on. So this will look like a slightly odd shape. It will look like you will have this one and then you will have a 0 point here, right? Because the middle one, which is the self correlation part, will be 0 and then it will continue like this. So basically this will be 0 because there is no self correlation. Okay, so that's the meaning of it. So its autocorrelation is a triangle shaped coefficient function. That's what exactly this one. But the central vertex amplitude, that means this center one will be 0. So there will be a dip at the center and then you will have a sort of a triangle on both sides. So that's the meaning of it. So if you're not understanding, I will just repeat it again. Intuitively, if you think this one, this particular function, the correlation between the transducers looks like you are doing an auto correlation, except that you are not doing self correlation, as well as repetitive ones are avoided. And the function, if you theoretically consider the function, let's assume that all transducers are weighted equally. That means it looks like a rectangular window, and then autocorrelation between rectangular window with itself is like a triangle function, and the triangle function in this case will have a 0 at the vertex at the center because you are not doing self correlation. That's the meaning of it. Now it goes back to the same. Even though I'm not putting an explicit weight wik here, this will look like a triangle function if I'm not doing any explicit weight. So basically in the case of DMAS, you could assume that the correlation function theoretically is a triangular function, and then it is aided by the value, the similarity value within the between the transducers, not between the transducers. Okay, I hope it's pretty clear to you, this part. Okay, so let's move on. Some more details and some more interesting results. So let me read this line and then let's understand what is happening. So image lateral resolution will be improved as both the wavelength and the f number will decrease. Very interesting statement. Why so? Just think, just pause the video and just think why I'm putting this command, okay, or putting this line. Okay, I hope you understood it, and let me actually come back to this in a moment. Okay, so what I meant actually is we already discussed that when we do the multiplication operation, what is going to happen is we'll have a signal which is a 2f0, right? So this is our new signal. So f0 became 2f0 because f0 was the starting point, like in delay and sum. But then when we do this operation, it will go to sort of interestingly, as we saw it, 2f0, correct? So then what is going to happen in the wavelength part is imaginable to you, right? If the frequency is doubled, wavelength will become half, right? So the wavelength will decrease, and then that's really interesting. And then you will argue with me that if the wavelength is reduced, then of course the axial and the lateral resolution both have to change. But I only mentioned lateral resolution here, and there is no mentioning of the axial resolution here. There is a reason, because along with the f0 getting reduced to, increased to 2f0, the bandwidth also get sort of halved, right? Because you can imagine that the higher the frequency it goes, it becomes tightly packed. So then that effective Q factor sort of thing will not change much. So that means the axial resolution is not going to change, but lateral resolution, because the wavelength has reduced, it is going to get improved in the lateral direction, because the bandwidth is not going to affect the lateral direction. It is just dependent on the wavelength, right? If you remember our old calculations, you go back and see that the axial resolution is not changed because the bandwidth is also changing, and both bandwidth will get reduced by sort of half, and then there is no point, right? I mean, because effective increase in frequency is getting reduced with the reduce in bandwidth, and that's just cancels out each other, and you won't get any improved result in the axial resolution. But lateral resolution is not that case. And f number, if you go back and see the f number definition, f number is actually depth by aperture, and you can see that the aperture is effectively going to increase because you are doing cross correlation. So effectively, ideally speaking, you will have 2nc minus 1 number. If you do all correlations, you will have this sort of number. So effectively, the aperture is going to increase, and when aperture is increased, your f number is going to come down. And there is a importance of that also in terms of lateral, because aperture, wider aperture, that means it's sort of, you can think of your transducer length is increasing, that means that beam pattern is going to sort of get reduced, right? So that is the advantage that you are going to get out of it. So wavelength reduction, wavelength gets reduced to half, as well as the aperture sort of increases almost like double. So that means both is going to help you in having a better lateral resolution. Okay, so that's, I think I have it written here. Okay, I think some sentence is missing, I will correct that. So the wavelength is half with respect to dash, as the FDMAS beamform signal spectrum is ended at 2f0. I think 2f0 is missing here, sorry for that, I will correct it before uploading. At the same time, the number of elements in the new artificial aperture is increased. Okay, that's pretty clear, right? I mean, because instead of x1, you now having x1 x2 x1 x3, so many x1 x2 x3 x4 will become x1 x2 x1 x3 x1 x4 x2 x3 x2 x4. So much aperture spread is happening, and because of that, you can imagine that when the aperture increases, the size, the width of the transducer increases, your beam pattern is going to come down, right? So that means the resolution, lateral resolution, is going to improve. Okay, so that's the important aspect. And then of course better clutter and noise rejection will be achieved because of the correlation operation, because you can imagine that if x1 and x2 are similar, they will get enhanced. If x1 and x2 are not similar, dissimilar, the multiplication will always bring that value down, right? You can think of something like higher values get multiplied higher, it will increase, and lower values will further become lower, right? So that's the reason why clutter and noise rejection is improved. At the same time, the contrast resolution, when we say contrast resolution, is nothing but the ability to distinguish between two intensity levels in the image. Okay, so if two levels, two regions of the image are closer in intensity, then we won't be able to distinguish between them, right? But the moment they get separated slightly in the intensity, you can maybe able to distinguish between them. So that contrast resolution is much better in the case of delay, multiply, and sum, as you will notice in the images. The reason is also pretty simple, because you do have a multiplication, and that multiplication enhances, just like the second line says, it enhances the similar ones and suppresses the dissimilar ones. And then to go with it, the autocorrelation factor, that weighting, so the autocorrelation function, that triangular sort of apodization which is going to happen, will further help us in reducing the grating lobes and the side lobes to lower level. And as a result of this, your contrast resolution, because if you have the grating lobes higher, then you won't be able to distinguish between two regions which are separated by the grating lobe and the main lobe, right? So if that grating lobe value is reduced, then the contrast will become much better, because you will be able to distinguish those two regions. So that's exactly what I meant here. So the three, this is, I mean, we started off with a simple beautiful mathematical manipulation, which is nothing but you cross multiply the transducers, and we now are analyzing the importance of that. And now you will be able to appreciate such a simple algorithm, where we extended from a simple delay and sum to a simple delay, multiply, and sum, is actually giving you immense benefit of improved lateral resolution, then better clutter and noise rejection, and then of course the contrast resolution is also improved a lot. Okay, so that's the important aspect. Okay, so I corrected that 2f0 thing here. Okay, now let's move on, and now it's time to see some results, because I've been talking a lot about all these. Now is it really coming in the results? We have to see that. Okay, so let me actually show you some examples. So this is something like a wire phantom, where we insert some wires which looks like point targets, some metallic wires you could imagine, in various depths. So the axial distance is here, the depth is here, and the lateral distance is here. And then this is a noise added case, so you will add some sort of scatterers also inside the phantom, inside the model, so that some noise scattering effect of ultrasound will also happen. Okay, so this is with respect to the ultrasound imaging, and this is taken from the second reference over here. So you can actually see very clear. So you can see that the lateral resolution, axially there is not much change that you could observe, but the lateral spread, so this is laterally spreading a lot, but then these guys are more confined in the lateral direction, particularly here this one. If you see over here, there's a lot of lateral spread which is actually sort of not there in this DMAS result. And you can see the all the results are normalized in this dynamic range. And of course, just like the receiver chain that we discussed in the DAS, the beam formation is followed by envelope detection and log conversion. Don't forget that that is standard, and for DMAS also you have to do that. And these results are actually the final image, which is log converted and envelope detected beam formed image. Okay, so that's the result that you are seeing over here. And even in the noisy case, you can see that the result is much better. Even you can see the contrast between these two. The speckle is at some gray level compared to a dark level, so the difference between the pin and or the wire and the speckle is much lower here compared to here, because you can see over here this background is almost dark, right? So that means the contrast resolution is also improved a lot. So now this is another result. So this is like a cyst which we created. Cyst is something like a let's say blood vessel, which is actually carrying lower number of scatterers compared to outside region. And then you can actually see over here, so compared to these two, you definitely can see that the distinguishability, the contrast is much better. And if I plot a line, okay, a horizontal line, in fact this is lateral distance, so a line like this in the image, a line like this in this image, and a line like this in this image. And if I plot the result over here, the black one is the DMAS, so you can see that the range, the distinguishability, the contrast is much higher compared to the DAS algorithm, which is actually in the gray color, which is shown over here. So understandably this is very important, and this helps in better interpretability of the result. So a very simple algorithm, very simple extension, you are multiplying the transducers across and then summing it up, that's what delay, multiply and sum, is giving you better lateral resolution and better contrast resolution compared to delay and sum. And why this is known as a non-linear beamforming algorithm is very simple, because multiplication is a squaring operation and squaring operation is a non-linear operation. So that's the reason. Okay, so if somebody is confused why I call at the start this is a non-linear beamforming algorithm, the reason is very simple, because you're squaring the signal, and of course you're taking square root, so that is just to make it amplitude signal, but effectively you are sort of multiplying, so that means a non-linear operation. This is another realistic result. This is carotid. So hope you might have heard about carotid. It is an important artery which is supplying blood to the brain. So most of the time, if this gets blocked, you will have lack of blood supply to the brain, resulting in stroke sort of condition. So this is an important landmark to check for. Let's say you have an accident and all, you most probably the doctors will immediately check this region to understand the blood flow which is going to the brain, if it is really going through or it is stuck. Okay, so this is the carotid vessel, the artery that you can think of, which is sort of a cross-sectional view. And this is basically the region that I'm interested in. And then all these things that you are seeing over here, the bright lines will be some muscle interfaces and blood vessel interfaces and so on. And very easily you can between these two you can decide that this is having better contrast, which is very evident. And even lateral resolution may not be that significant in this case, because you have a continuous structure here, and maybe some regions like this, if you see, you can see that clutter is less, and you can see that there is a lot of resolution improvement also happening. So that's it for this particular lecture. So here we introduce a takeaway. Here we introduced a very simple concept of delay, multiply and sum. So let me actually put in terms of expression here so that it's very clear to you, and we'll conclude this lecture. And in fact I will only put this video for this week, and we will continue with another type of beamforming algorithm in the next week, and then transmission imaging also will couple in the next week. Okay, so basically let me put this way: y dash of k is nothing but you vary from 1 to NC, where NC is a number of transducers. You need to weight WIK corresponding to ith transducer and kth pixel, and then of course SIK of T. Let me put that way. Okay, and this is as implies this is nothing but k of T minus tau ik is the literal meaning of this guy. Okay, so that is dash, and then of course d mass is, you have two summations. One is actually going from 1 is to NC minus 1, and then second one is going from 1 I plus 1 to NC, and then you have SIK SJK, that I can't simply do that. So what we need to do is we need to put sign of this guy, so sign of this product multiplied by the absolute and then square root of it. So XIK SJK, that product I will do, and then take the absolute of that, then take the square root of that, and then multiply that with the sign of this. So this is the expression. So delay, multiply, and sum compared to delay and sum. And then the advantages are lateral resolution is improved, noise and clutter is removed, and contrast resolution is improved. And then of course the important aspects that you have to turn is there is a natural apodization happening because of the cross correlation function, and that is actually going to help you in this contrast resolution improvement and so on. Okay, so with that I hope you enjoyed this lecture. Very important algorithm, and in a typical standard course on sensor arrays and imaging this may not be covered, but I thought since all of you are MTech and above, it's important that you understand there are some advanced concepts beyond the delay and sum available, which are very important to improve the image quality. Okay, so with that I will stop this lecture, and see you all in the next week, and where we will continue with another adaptive data driven beamforming algorithm. So when we say data driven beamforming algorithm, we are not going to change the delay compensation part. That part remains same, only the apodization is changing. In this case also delay compensation remains same, only the apodization became sort of naturally driven by the cross correlation or auto correlation, right? So that's it. So bye from my side, see you in the next week.